Hello, everybody. Welcome to the session. My name is Ming-Yu. I'm a researcher at Nvidia. My talk today, titled Face-VID2VID. I'm gonna talk about our CVPR paper on one-shot free-view neural talking head synthesis for video conferencing. I will introduce our talking head synthesis model that is person agnostic, that can synthesize a person based on a photo of the person, and its applications to video conferencing. At this point, we know that video conferencing has become a major part of our life. People spend tremendous amounts of time using video conferencing app communicate with their colleagues, friends, and family. Just last week, I spent 20 hours using video conferencing app. And this also reflects in the stock price of Zoom. Just in 8 months, the stock price increased by 6 times. Although broadband assets has become more widely available, but as more people are using video conferencing app, bandwidth is still limited. Ideally, we want to have unlimited bandwidth that we can accommodate as many people as possible. Also, infrastructure could be poor. Not everywhere has broadband access. Not everywhere have high-speed internet. Still, a lot of regions in US have poor bandwidth. Outside United States, there are still many underdeveloping countries where broadband access does not exist. Also, the upload speed is often the bottleneck. You could have a faster download speed, but to have a video call with the other party, you need to stream your audio and the video. And if your upload bandwidth is limited, you still cannot have a good video conferencing call. And there's also eye contact issues. We tend to look at the person in the screen instead of looking at the camera, and this creates the eye contact issues. Although we are really look into the other person's face, but because we are not looking into the camera, it looks like we are not paying attention. Unfortunately, this has been a well-recognized issue. Several companies, including Intel, Microsoft, Apple, they all have some in-house solution that can correct the gate. Although you are looking at your screen, not looking at your camera, the receiver will receive a video stream that's like you are looking at the camera. Many of us have dual screen system, and we often mount webcam on one screen. Sometimes when we have video conferencing, the window that display the other person could be in a screen different to the screen with the webcam, and then we appear not look to our friends or colleague in the face and lack of eye contact. Although the gate correction techniques that we show in the previous slide can more or less change the gate, however, the degree of correction may not be sufficient to have proper face-to-face talking experience. Instead of just changing the gaze, we might also need to rotate the face to look at the receiver. And these are some issues we have in mind when we were developing the Face-VID2VID method that we're gonna talk about today. So, what does this Face-VID2VID algorithm achieve? In the top left is the input video uncompressed. And here we show two comparison results. One uses the H264 standard. The other is using the Face-VID2VID algorithm. When operates at the same compression rate, and we found that the H264 give you pretty blurry results, while our methods give you almost identical result to the input. And in the bottom left, we show how we can use the Face-VID2VID algorithm to change the face direction to simulate eye contact. So this could potentially work for a reasonable degree of rotation. So the double screen, double monitor system is no longer an issue. The Face-VID2VID algorithm can also be used for photo animation. Given a 2D photo of an avatar of a person, we can drive the motion of that avatar using the input video. So pretty much transferring the motion from the subject to the character. And we're gonna show more results and how we achieve it in the following slides. So our method is based on a neural token head model, and there are many different neural token head models, and we can roughly divide them into 4 categories. So there are 2 ways to divide them. One is whether this model is person specific or person agnostic. Person specific means that the model can only work for the person used in training. Person agnostic meaning that it can use to a wide range of people. And based on whether to use 3D models of the person, we can have models that's based on 3D and a model that's based purely on 2D. And our model is in the category of person agnostic and pure 2D. And it's important to know that for video conferencing, we actually prefer person agnostic model, a model that can be used by all the people. Of course, we can argue that for person-specific model, it's easier to achieve better performance because all the network bandwidth is located for that person. However, in terms of deployment, it's more inconvenient because you need to train a model for each person, and training is still require more attention than inference. That's why we built our model based on person agnostic model. In this slide, we're gonna show you the breakdown of the steps in Face-VID2VID. Let's say we have a video. We want to send from the sender to the receiver. We'll take the first frame and call it source image. For the source image, we're gonna extract appearance information. Then all the other images in the driving video, we will extract expression and hypos information. Now, by combining the appearance and expression hypos information, we can reconstruct the input video. If you don't like the hypos in the input video, you can specify your preferred hypos, and this can be used for the face redirection application. And we're gonna call the expression and the head pose all blend together as key points. And the key points are just a small number of numbers. They are easier to compress compared to the driving video, to each frame of driving video. And this is how we can achieve much better compression rates as compared to the H264 standard. Now, if you use a 2D photo of another person instead of this person, then the appearance information gonna be from a different person. And by loading the expression head pose from the driving video, we transfer the motion from the person in the driving video to the new person in the source video. And this can be also a 2D avatar. Then we can this can be used to achieve the avatar animation, like the example you show, like we showed you earlier. The key for this Face-VID2VID algorithm is to build good correspondence. Whatever information you can borrow from the source image, you should learn to borrow through some correspondence learning during training. And there will be places where you cannot borrow. You have to hallucinate. For example, in the new frame, the subject might close their eyes, and you never see the appearance of closed eyes for this subject. So the network need to hallucinate. And by training the network using a huge number of videos, some people gonna have their eye closed in the video. Then you can learn the closed eye patterns from those videos. So when this person, although you didn't see the person with closed eye, but you have seen others, then the network know how to hallucinate closed eye for the person. Here we are going to describe the high-level operation of the Face-VID2VID. For the source image and driving image, through a set of processing, eventually we will get two sets of key points, two sets of 3D key points, one for the source image, one for the driving image. These key points specify the location of the facial feature in 3D. And through these two sets of points, we're gonna infer 3D flow. This can be used on how we're gonna borrow features from source to driving for the reconstruction. So now we train the source feature and use the 3D flow to warp the source feature to have a warp feature, and feed into the generator to reproduce the driving image. So for the scenes that cannot be borrowed from the source images, from the source feature, the generator cannot hallucinate that. In the processing, we actually also use occlusion map for infer the location to help guide the generator to know when to hallucinate. Okay, now in the next slide, we're gonna dive into the details on how we estimate the 3D source key points and 3D driving key points. So we use a specific key point decomposition scheme for estimate the components and combine them to obtain our final 3D key point representation. We have two branches, the identity branch and the pose branch. We use something we call its canonical key point detector to extract identity information. The canonical key points encode the person identity only, such as the shape of the face, mouth, nose. It doesn't contain pose or expression information. And pose and expression is extracted through this pose expression estimator. So this gives us the head rotation angles, 3 numbers, head translation vector, 3 numbers, and expression deformations, a set of vectors that represent the deviation of the canonical key point due to expression. Now, by combining the canonical key points with this head rotation angle, head translation vector in expression deformation, we have the 3D source key points. And for the driving image, since we expect coming from the same person, we don't need to extract the identity information again. So we just apply the post branch to extract the head rotation angle, head translation vector, expression deformation. And by combining with the canonical key points from the source images, we have driving key points, the 3D driving key points. And as shown in the previous slide, we use source key points and driving key point to build out a correspondence to warp the source features. And just to notice that we only have one post and expression estimator. We use the same one for the source image and for the driving image. Now let's visualize the steps of this key point decomposition and the reconstruction. For the source plane, we extract the canonical key points, which represent the canonical view of the subjects. For the driving frame, the driving image, we extract head rotation angle, head translation vector, and expression deformation. Okay, now let's show how these quantities change the reconstruction. Apply the head rotation, we rotate the person to the right angle, and apply the translation, we put the head in the ideal location, and then we apply the expression, then we reconstruct the face. Now let's illustrate how we can build a video conferencing system using the proposed algorithm. Recall that in video compression algorithm, there's an iframe which is compressed using the regular image compression mechanism, and that's a pframe which is based on residual encoding and motion estimation. So we in our system, in our neural token heads model, we have a source plane and the driving image, right? The source plane will be treated as iframe, and they will be sent using the regular image compression algorithm. Now, for the driving image, instead of coding them using the pframe, we're gonna use our network to extract the expression and head pose information. Now we extract the rotation and translation of the head pose, and also the expression deformation. And this is just a bunch of numbers, and usually we use 20 key points. So then there will be 20 key point deformations. Each one is 3-dimensional, so there are 16 numbers here. Rotation 3 angles, translation 3 quantities, 3 scalars. So totally 66 numbers. And this 66 number can be further compressed using an entropy encoder. We use an arithmetic encoder in our paper, but Huffman coding is equally applicable. So this is what happened in the sender side. In the receiver side, it's first use the entropy decoder to get back the rotation, translation, and expression deformation. And now combined with the source features extracted from the source images and also the canonical key points, we can reconstruct the driving image. And if you don't like the head pose, you can specify your own. And because this rotation, translation, deformation, expression deformation are such a small set of numbers, it's very easy to compress, and that's how we can achieve high compression rates over H264. We compare our neural token head-based video conferencing system with H264 and 265 and other baseline algorithm for video compression performance. So here are the experiment results. We show three figures. In the first figure, the x-axis is the bits per pixel, the amount of bits required to transmit videos in average. The y-axis is the LPIP score, a perceptual distance metric. So the lower the LPIPs, the better performance. So ideally, we want some point in the bottom left corner, low bit rate and low perceptual distortion. Okay, H264 has a parameter to control the trade-off between the reconstruction quality and the bandwidth consumption, called CRF, constant rate factor. So we vary the number from 32 to 50 and report the performance of H264 here. And similarly, we do the same for H265. And we also compare to a couple of baseline algorithms. One is the first order motion model. Similar to our method, it also uses key points, unsupervised learned key points. And also our previous method called Face-VID2VID, based on landmarks iterated by some landmark iteration algorithms, usually 68 landmark points. And we also apply entropy coding to the landmarks as well as a key point iterated by first order motion model, the same entropy coding scheme for fair comparison. And we have two variants. One is a version where we use 20 key points. Another is we call adapt. So basically, we send fewer key points when the videos are easier to reconstruct, and this is done automatically. So there's a mechanism to determine when to send more key points, when to send few key points. So this one achieves slightly better compression rates compared to our methods. And as shown in this figure, we find that our method is significantly better than the baseline algorithm F first order motion model and Face-VID2VID, and also much better than the codec H264 and H265. We also conduct a user study to compare video quality produced by H264 and ours. So we do a A/B test and ask a bunch of mechanical Turkers to choose which one better reproduce the input video, and this is the preference score. And so we compare our, which is a single point, to different set of video produced by different CRF numbers of H264, and we find that our method is roughly comparable to 36, and 36 is about 0.016784 bits per pixel, and ours is about 0.001618, so about 10x improvements. We also conduct experiments, the same user study, but this time with H265, and ours is comparable to H265 on 37, and so it's around this place. So compared to H265, we didn't achieve 10x gain, but still quite significant. Here we show how we can achieve better eye contact by simultaneously rotate face and gaze. And it's a user interface easy to control to get the specific look you like. So we also experiment our method in the task of animating photos generated by StyleGAN. So StyleGAN generates a convincing photo of a subject, and we use this Face-VID2VID to animate the subjects. Also want to mention that the driving video can also come from a CG rendering. Here we have a CG rendering that's produced by Nvidia audio to face framework. It produced this we call it digital mark, speaking something, and we use the motion here through the Face-VID2VID to animate StyleGAN faces as well as a couple of real photos.
We're going to play a wonderful game called Who is Your Daddy and What Does He Do? We're going to play a wonderful game called Who is Your Daddy and What Does He Do?
Conclusion. So Face-VID2VID is a neural talking head model for video conferencing. It achieves great compression rate and can achieve face and gaze redirection as well as photo and 2D avatar animation. The code is built using the imaginary repo, and the model will be available at this Machine website, and the online demo is available at this website. I would like to thank you for your time and for the questions.